How surprising was it to you, because you were in the middle of it,
Mm-hmm.
how effective attention was?
Self-attention.
Self-attention,
Yeah.
the thing that led to the transformer and everything else, like this explosion of
Yeah.
intelligence that came from this
Yeah.
idea. Maybe you can kind of try to describe which ideas are important here, or
Yeah.
is it just as simple as self-attention?
So I think first of all, attention, like Joshua Bengio wrote this paper with Dimitri Badano called Soft Attention, which was first applied in this paper called Align and Translate. Ilya Sutskever wrote the first paper that said you can just train a simple RNN model, scale it up, and it'll beat all the phrase-based machine translation systems. But that was brute force. There's no attention in it. And spent a lot of Google compute, like I think probably like 400 million parameter model or something, even back in those days. And then this grad student, Badano, in Bengio's lab, identifies attention and beats his numbers with way less compute.
Mm-hmm.
So clearly a great idea. And then people at DeepMind figured that, like this paper called Pixel RNNs,
Mm-hmm.
uh, figured that you don't even need RNNs, even though the title is called Pixel RNN. I guess it's the actual architecture that became popular was WaveNet, and they figured out that a completely convolutional model can do autoregressive modeling as long as you do mask convolutions. The masking was the key idea, so you can train in parallel instead of backpropagating through time. You can backpropagate through every input token in parallel. So that way you can utilize the GPU compute a lot more efficiently because you're just doing matmos.
Mm-hmm.
And so they just said throw away the RNN, and that was powerful. Um, and so then Google Brain, like Vaswani et al., that the transformer paper, identified that okay, let's take the good elements of both. Let's take attention. It's more powerful than cons. It learns more higher order dependencies because it applies more multiplicative compute. And let's take the insight in WaveNet that you can just have a all convolutional model that fully parallel matrix multiplies and combine the two together, and they built a transformer. And that is the, I would say it's almost like the last answer, that like nothing has changed since 2017 except maybe a few changes on what the nonlinearities are and like how the square root descaling should be done. Like some of that has changed, but and then people have tried mixture of experts having more parameters per for the same flop and things like that, but the core transformer architecture has not changed.
Isn't it crazy to you that masking, as simple as something like that, works so damn well?
Yeah, it's a very clever insight that look, you want to learn causal dependencies, but you don't want to waste your hardware, your compute, and keep doing the backpropagation sequentially. You want to do as much parallel compute as possible during training. That way, whatever job was earlier running in 8 days would run like in a single day. I think that was the most important insight. And like whether it's cons or attention, I guess attention and transformers make even better use of hardware than cons because they apply more compute per flop. Because in a transformer, the self-attention operator doesn't even have parameters. The QK transpose softmax times V has no parameter, but it's doing a lot of flops. And that's powerful. It learns multi-order dependencies. I think the insight then OpenAI took from that is, hey, like Ilya Sutskever was been saying, like unsupervised learning is important, right? Like they wrote this paper called Sentiment Neuron, and then Alec Radford and him worked on this paper called GPT-1. It wasn't even called GPT-1, it was just called GPT. Little did they know that it would go on to be this big, but just said, hey, like, let's revisit the idea that you can just train a giant language model and it will learn natural language common sense. That was not scalable earlier because you were scaling up RNNs. But now you got this new transformer model that's 100x more efficient at getting to the same performance, which means if you run the same job, you would get something that's way better if you apply the same amount of compute. And so they just train transformer on like all the books, like storybooks, children's storybooks, and that got like really good. And then Google took that insight and did BERT, except they did bidirectional,
Hmm.
but they trained on Wikipedia and books, and that got a lot better. And then OpenAI followed up and said, okay, great. So it looks like the secret sauce that we were missing was data and throwing more parameters. So we'll get GPT-2, which is like a billion parameter model and like trained on like a lot of links from Reddit. And then that became amazing, like, produce all these stories about a unicorn and things like that, if you remember.
Yeah, yeah.
And then like the GPT-3 happened, which is like you just scale up even more data. You take Common Crawl and instead of 1 billion, go all the way to 175 billion.
Hmm.
But that was done through analysis called the scaling loss, which is for a bigger model, you need to keep scaling the amount of tokens, and you train on 300 billion tokens. Now it feels small. These models are being trained on like tens of trillions of tokens
Hmm.
and like trillions of parameters. But like this is literally the evolution. It's not like then the focus went more into like pieces outside the architecture on like data, what data you're training on, what are the tokens, how deduped they are, and then the chinchilla insight that it's not just about making the model bigger, but you want to also make the data set bigger. You want to make sure the tokens are also big enough in quantity and high quality and do the right evals on like a lot of reasoning benchmarks. So I think that ended up being the breakthrough, right? Like this, it's not like attention alone was important. Attention, parallel computation, transformer, uh, scaling it up to do unsupervised pre-training, right data, and then constant improvements.
Well, let's take it to the end because you just gave an epic history of LLMs and the breakthroughs of the past 10 years plus. So you mentioned GPT-3, so 3.5. How important to you is RLHF, that aspect of it?
It's really important. It's even though you call it as a cherry on the cake,
This cake has a lot of cherries, by the way.
it's not easy to make these systems controllable and well behaved without the RLHF step. By the way, there's this terminology for this. It's not very used in papers, but like people talk about it as pre-train, post-train.
Mhm.
And RLHF and supervised fine-tuning are all in post-training phase, and the pre-training phase is the raw scaling on compute. And without good post-training, you're not going to have a good product. But at the same time, without good pre-training, there's not enough common sense to like actually have, you know, have the post-training have any effect. Like you can only teach a generally intelligent person a lot of skills, and that's where the pre-training is important. That's why like you make the model bigger. The same RLHF on the bigger model ends up like GPT-4 ends up making ChatGPT much better than
Mhm.
3.5. But that data, like, oh, for this coding query, make sure the answer is formatted with these markdown and like syntax highlighting, tool use, and knows when to use what tools.
Mhm.
You can decompose the query into pieces. These are all like stuff you do in the post training phase, and that's what allows you to like build products that users can interact with, collect more data, create a flywheel, go and look at all the cases where it's failing, collect more human annotation on that. I think that's where like a lot more breakthroughs will be made.
On the post-train side,
Yeah.
post-train plus plus. So
Yep.
like not just the training part of post-train, but
Yeah.
like
Yeah.
a bunch of other details around that also.
Yeah. And the RAG architecture, the retrieval augmented architecture, I think there's an interesting thought experiment here that um, we've been spending a lot of compute in the pre-training to acquire general common sense, but that seems brute force and inefficient. What you want is a system that can learn like an open book exam. If you've written exams in like in undergrad or grad school where people allowed you to like come with your notes to the exam versus no notes allowed, I think not the same set of people end up scoring number one on both.
Mm. You're saying like pre-train is no notes allowed.
Kind of, it memorizes everything. Like
Right.
you can ask the question, why do you need to memorize every single fact to be good at reasoning?
Yeah.
But somehow that seems like the more and more compute and data you throw at these models, they get better at reasoning. But is there a way to decouple reasoning from facts? And there are some interesting research directions here. Like Microsoft has been working on this phi models, where they're training small language models. They call it SLMs,
Mhm.
but they're only training it on tokens that are important for reasoning. And they're distilling the intelligence from GPT-4 on it to see how far you can get if you just take the tokens of GPT-4 on data sets that require you to reason, and you train the model only on that. You don't need to train on all of like regular internet pages. Just train it on like basic common sense stuff. But it's hard to know what tokens are needed for that. It's hard to know if there's an exhaustive set for that. But if we do manage to somehow get to a right data set mix that gives good reasoning skills for a small model, then that's like a breakthrough that disrupts the whole foundation model players, because you no longer need that giant of cluster for training. And if this small model, which has good level of common sense, can be applied iteratively, it
Mhm.
bootstraps its own reasoning and doesn't necessarily come up with one output answer, but thinks for a while, thinks for a while. I think that can be like truly transformational.
Man, there's a lot of questions there. Is it possible to form that SLM? You can use an LLM to help with the
Yeah,
filtering which pieces of data are likely to be useful for reasoning.
absolutely. And these are the kind of architectures we should explore more, uh, where small models, and this is also why I believe open source is important, because at least it gives you like a good base model to start with, and try different experiments in the post training phase to see if you can just specifically shape these models for being good reasoners.